This is part of the ASTER digital topography data set, and then the color image that's draped over it is also derived from ASTER optical data. The speed we'll fly at is about the time it actually takes the satellite to cover the same amount of distance. At the bottom is the island of Catalina with some clouds on its southern shore. We turn over the Palos Verdes Peninsula and the LA Basin, the downtown area. We're pointing directly now at the San Gabriel Mountains and the Jet Propulsion Laboratory where I'm sitting right now. The sharp boundary between mountains and desert is the San Andreas Fault. The San Joaquin Valley, the Great Valley as it's called, occupies most of the state of California. The San Andreas Fault, a sharp trench, forms the boundary between the Pacific Plate on the west and the North America Plate on the east. So we take two images of the same area at slightly different look angles, just like your eyes do, and then we can calculate the relative distance based on how much the image appears displaced, each part of the image. So it's exactly the same way your brain constructs three dimensions. We can calculate the relative distance, and from that we can then calculate the topography for every point that we image. So one priority we have is to systematically image all the active volcanoes in the world, and that's about 1,200, and we image them at least 2 times a year, and some of them up to 10 or 15 times. Similarly, we have a program to image all the glaciers in the world, and that's on the order of 10,000. So we've been doing that for 10 years, and that has led us to be able to look at not only the decadal change in, for instance, glaciers retreating or advancing, but also yearly changes, fluctuations.